Hello all, and welcome to this Eyes to the Sky video on calculating storm relative helicity. In this video we're going to go through some of the basics of how to calculate storm relative helicity, basically what it means, the implications for using it in operational forecasting, and some of the drawbacks of storm relative helicity and its pros and cons. So we'll jump right on in now. I'm excited to present this video. This is one I've been working on for a while and have been trying to determine exactly how to present this information because I feel that storm relative helicity is an indice within the meteorological community that needs some explaining and not necessarily some improvement, but just maybe some adjustments in wholesale understanding in some aspects, but it is a fascinating variable, and let's jump right on in and discuss it. What is storm relative helicity? Storm relative helicity is the amount of rotation potential or streamwise vorticity available to a thunderstorm, with the motion of the thunderstorm itself as one of the main components of the calculation. Storm relative helicity was developed in the late 1980s and early 1990s by Robert Davies Jones. Storm relative helicity consists of three components. Number one, the forward speed and direction of storm motion. This provides the storm relative component to storm relative helicity. Number two, the amount of wind speed change with height. This is known as speed shear. And number three, the amount of wind direction change with height. This is known as directional shear. Storm relative helicity is generally calculated to a max height of 3 kilometers, as this is commonly accepted as the depth of the storm inflow layer. Storm relative helicity is a rather complex calculation that can be drastically simplified using something called the layer centering technique, which provides a very strong estimation of storm relative helicity. We will cover the technique in this video. Some common misconceptions. Number one, the sounding profiler observed storm relative helicity, for example, is 350 meters squared per second squared, but the surface winds are too southwesterly. Therefore, we can't have tornadoes in this environment because there's not enough turning. This is a myth because typically the value should be taken or used operationally as is. So the value should just be taken for what it's worth directly, just as the integer alone. Thompson from 2005 even suggests that 0 through 1 kilometer bulk shear can be used as a better metric for indicating tornadic potential. Number two, use caution when using storm relative helicity as a proxy for TOR, no TOR in a forecast. There are many ways the atmosphere can increase chances of tornadogenesis, even in the presence of weak storm relative helicity values. These include mesoscale baroclinic zones within the planetary boundary layer, interactions with nearby storms, such as intrastorm or interstorm processes. Storm relative helicity is highly Storm relative helicity is highly variable within space and time and is a necessary but not sufficient condition for tornado formation. Number three, large clockwise hodographs determine the potential for right-moving storms. This is something that is highly debatable. I mean, it's known that large clockwise hodographs are conducive for right-moving storms, but there's more detail that's needed. So although there may exist a loose correlation between large curved hodographs and right-moving storms, additional discriminating requirements have been identified regarding the balance between basal or non-deviant storm motion and distribution of speed and directional vertical wind shear. Here's the layer centering technique for calculating storm relative helicity. This is something I've been working on over the past 6 months. It's an interesting way of looking at things here. Three things are needed, and this is for any storm relative helicity calculation. Number one, the storm motion. This is the storm relative part of SRH. Number two, the amount of speed change with height or speed shear. And number three, the amount of turning with height or directional shear. First, you must determine how deep the buoyancy or cape profile is for your particular case. Once you find this, then find the center of the buoyancy profile and include an area approximately 100 millibars above and below this centered point of the buoyancy profile. This becomes the layer in which you will average wind speed and direction in order to obtain the storm motion coefficient for the storm relative portion of the calculation. Other ways you can obtain storm motion are use the bunker storm motion method, simply by the 700 millibar wind, and using radar observations. And this last one, the last bullet point, works mainly in post-analysis in trying to analyze past cases using reanalysis data or radar data. You can take the actual observed storm motion, speed and direction using radar, and then use that for your storm relative portion of storm relative helicity. So using the observed sounding on the right, this is from April 27th, you can see that in order to find the layer center, you want to find the upper bound of the buoyancy profile, or the equilibrium level. That's up here at 150 millibars in this case. Then you want to look down here to where the LCL is. It's down here, looks like at about 915 millibars. And so from there you want to go into the middle of the buoyancy profile. That would be the layer center, and then go 100 millibars above and 100 millibars below that layer, and average the wind speed and direction, and that will give you your storm motion component. We'll go into more detail on how to calculate that in just a moment. So the layer centering technique equation, A is the storm motion. This is the compass direction the storm is coming from, multiplied by the speed of the mean wind. This equals the storm motion coefficient, or the master coefficient. If speed of the mean wind is not known, but speed of the storm is known, for instance from radar observations, etc., simply divide the known storm speed by 0.75 or 75% to get the approximate speed of the mean wind. This comes from the research of Maddox from 1976, where he discovered the empirical guidance of 30R75, or 30 degrees to the right of the mean wind at 75% of the speed. This is a solid way to obtain the mean wind, and we will see that in the layer centering technique we're discussing. Part B is the change in speed in knots multiplied by the change in direction degrees. Once this quantity is obtained, simply multiply it by 12.5 to calculate helicity. However, remember that this value is not yet storm relative because we have not yet added in the storm motion component from part A above. And then finally, C, A plus B times 0.0093 equals SRH. This will produce a very accurate calculation of storm relative helicity for a wide range of atmospheric cases. So here we're going to do an example of the layer centering technique. Number one, the mean wind of 253 degrees was observed at 84 knots in the April 27th case at Wright. Again, this is from using the layer centering technique that we discussed earlier, and now you know how to apply that. Simply multiply 253 by 84 to get what I call the storm motion coefficient. So 253 times 84 equals 21,252. Then simply determine how much the wind speed changes from the surface up to the level you want. For instance, at Wright, we have 24 knots at the surface down here and 77 knots at 3 kilometers. So that produces 53 knots of bulk shear. And again, bulk shear is just the change in wind speed between two layers. So between the surface and 3 kilometers in our case, the wind speed change is 53 knots. Part 3, next find the number of compass degrees that the wind veers within the same layer, or between the surface and 3 kilometers in our case again, since that is the layer that we're calculating. And in this case, it is found to be 45 degrees between here and here of veering. Remember, veering again is the clockwise turn of wind with height or time or horizontal distance in meteorology. Part 4, multiply the amount of bulk shear, again found to be 53 knots, by the amount of veering with height, which was 45 degrees. So 53 times 45 equals 2,385. Then multiply this value by a constant of 12.5. So 2,385 by times 12.5 equals 29,812.5. Finally, in part 5 below, just add the results from steps 1 and 4 together and multiply this quantity by 0.0093. So finally, we have 21,252 plus 29,812.5. All of that quantity added together times 0.0093 gives us a final value of 475, which when we compare that to the balloon radiosonde observation of 502, we see that that is within 95% accuracy of the actual balloon observation from the Birmingham sounding 0Z April 28th, 2011, 7 p.m. April 27th in Birmingham. So there may be a slight discrepancy here. There is, obviously, by 27 meters squared per second squared, and the cause behind that could be a storm motion estimate that's just a little different from what they used in their calculation from the bunkers method, which is typically, I believe, what the National Weather Service uses for their storm relative helicity calculations. So very, very close. But I wanted to run this example by you just to show you how the layer centering technique for calculating storm relative helicity actually is applied. So with that said, I want to go into how storm relative winds are really what matters in the atmosphere when analyzing tornado potential. All of these images are from Markowski and Richardson from their 2005 paper on the classification of vertical wind shear as directional shear versus speed shear. This is from the April 2006 Weather and Forecasting issue. Note how vastly different wind profiles can have the same storm relative wind profile. This is really fascinating. And in the example on the upper left here, this is from Athens, Georgia on March 27th, 1994 from the Palm Sunday tornado outbreak. I'm sure many of you have probably either heard of or studied this event. But notice how the ground relative winds, again, the ground relative winds are just the wind profile taken as gospel word, or just taken as given by the by the balloon sounding or by the profiler system, the VAD. So this is just what you'll see when the balloon sounding comes out, just as is. But look how different the storm relative wind profile is when the storm motion component is factored in to the equation. It changes the wind profile vastly. So here you have a south-southwest wind at the surface from the pure observations from the ground relative profile, but when you do the storm relative analysis, notice how you have an easterly wind, or even slightly north of east, and then you have tremendous veering with height all the way through the column, at least up to 6 kilometers. A classic supercell storm relative wind profile is then created. And this is a profile from March 31st, 1985 from Pittsburgh, Pennsylvania. Many of you know that outbreak as well. That was the United States-Canada tornado outbreak, May 31, 1985. Notice here our ground relative winds, our observed winds are even more southwesterly at the surface. And then we have a rather quick veering and not much veering above 3 kilometers. And so then when we do the storm relative analysis, taking into consideration again the storm motion, notice how that changes. Your surface wind, storm relative inflow, the storm relative wind is vastly from the southeast. And then you have continued veering through a large part of the profile, but a more steady veering, which is more indicative of supercells. And here's some modeling analysis that Markowski and Richardson did. Notice these two ground relative wind profiles that they ran model analyses on. Notice how this one is purely unidirectional. You just have speed shear with height. And then you have one that has both speed and directional shear with height. But notice how they have the same storm relative wind profile. So this is something to get you to chew on, how you can have vastly different observed wind profiles also known as ground relative wind profiles, that have the same storm relative wind profile. And this is very important, folks, for understanding a tornadic environment. So my goal here is to try to get us all to understand that the storm relative wind profile is what really matters. So when next time you go on your chase trip or you're forecasting, go ahead and try to get in the storm relative framework immediately, and know that you can have a unidirectional wind profile but still have a storm relative wind profile that is highly conducive for the development of even violent tornadoes, which is hard to believe, but it is certainly possible. Just by shifting the hodograph away from the origin just a little bit, even a straight line hodograph can have vast tornadic potential if the storm motion is in such a way that that can occur. So just to wrap up, this has just been a little summary of storm relative helicity and some ways to apply it. And I hope you've gotten a lot out of this video. And if you have any questions or comments, of course, just post them and I'll try to get back to you. So I sure appreciate it, and y'all have a great day.